Chapter 11, SIR Model Part 2. Just to return to the problem we had in the previous video, let's suppose we have 490 susceptible individuals, 490 that can catch the disease. 10 infections are introduced into this population of 500. None recovered, so we're starting our experiment in the beginning. This coefficient over here we looked at, we calculated to be 0.00092. What goes into it is the basic reproduction number, the infectious period of 5 days. In the bottom, that's the total population. S is 0 plus I is 0 plus R is 0. A person has to fit in any one of these three categories. That's 500 in this case. 2.3 divided by 2,500 is 0.00092. Now 1 over tau went right here for new recoveries. 1 over 5 is 0.2. So I just built these constants into the table. You could put the formula up here if you wanted, but it would be, as we follow through the model, it's constant. It stays constant. It does not change. So first of all, we calculate new infections. We're multiplying 0.00092. That was the C in the logistic model, times the number of possible interactions between somebody that can catch it and somebody that has it. 490 times 10 is 4,900 possible interactions. Times this coefficient, we end up with 5 rounded. You can carry this to whatever place you want if you're doing the model. I just picked the average, the nearest person. And then we multiply 0.2 times the number of infected. Number of infected is 10, and we get 2. 10 infected for a duration of 5 days, and so 10 divided by 5 is 2. 2 per day makes sense. Then we come down to day 1, and S of 1 is going to be 490 minus 5. Okay, we have 5 infections, so these five of these susceptibles became infected. So this, oops, let me use the red marker. This is that 5 right there. And so we have 485. Now, as far as the infected, we have start with 10 infections. We add 5, but 2 recover. So 5 minus 2 is 3. It gives us 13. And the 5 and the 2 that we had are right here. That 5 and that 2 go right here. And we have no recovered, then we have 2 new recoveries. 0 plus this 2 ends up being this 2. So our new state of affairs is we have 485 susceptible, 13 infected, 2 recovered. And then what we do is we recalculate. 0.0092 times 485 times 13, 485 times 13 is equal to 5 rounded. 0.2 times 13, that's 2.6, which I round up to 3. And then we continue to the next day. 485 minus this 5 is 480. 13 plus 5 minus 3 is 15. And this 2 plus this 3 is 5. So now we have 5 recovered. And then we continue. Same thing for the next row. You can update these state variables and continue. That's the SIR model. I found various discrete forms of this, but for some reason, this coefficient, they like to parameterize this in terms of contacts and probability of a contact leading to an infection. That's an interesting way to do it. But I thought it would be more important to parameterize this in terms of this basic reproduction number in this infectious period tau. Those are 2 known parameters of various diseases, whether it be smallpox, chickenpox, measles, the seasonal flu, COVID, whatever. And we're going to, in part 3, we're actually going to look at what happens. What happens if we follow this down? You can't see much happening for the first 3 days, but what happens if we move into the future 3 months? What effect does varying this parameter have? Well, it's significant. Seasonal flu, it's kind of ho-hum what happens. COVID, if you use a reproduction number of 3, 4, or 5, it has serious consequences for the future. Same thing, even more serious if it's a reproduction number of 15, like the measles. So there you have it. It's pretty simple. If you wanted to do any serious modeling, of course, this is very easy to parameterize with a spreadsheet like Excel. If you have some spreadsheet skills, it's very, very easy to do this. And you can plug in these known parameters. You can look up these parameters. One of the things we mentioned before, there is a bit of uncertainty with these parameters. So especially if you look back through history, the methods by which these were calculated varied. And depending on what type of method you used, SIR method model actually is one method. You could vary this parameter until this forecast fits what actually happened and try to estimate it that way. It's very, very difficult to do in this case because a lot of things are changing, a lot of variables are changing. We have a serious outbreak, what happens? People social distance, they hike, they go to the mountains, whatever. And so I have actually seen very complex models that have adapted this for social distancing being rolled out. So the math modelers are always hard at work. So that's basically the SIR model. All it is logistic model with this added correction here. So that's all for this video. We'll be back with some Excel forecasts, part 3, so you can see the results of this.